Greetings and welcome, friends. Mr. Waddy here. We're taking a look at section 5.8 from our Big Ideas Geometry book. Today we are talking about proofs in the coordinate plane, where we're going to be thinking about these problems where we know all sorts of ways of proving triangles congruent. We perhaps remember how to show that lines are parallel or perpendicular, right, by relating their slopes to one another. We can prove segments are congruent using a distance formula, things like that. And we're going to be doing proofs on the coordinate plane. Now, this first part we're going to be jumping into is the idea of placing a figure on the coordinate plane, because it turns out if I'm doing a proof on the coordinate plane, I can set myself up for success or a significant amount of difficulty. And so we are going to try to set ourselves up for an easier time rather than one that is more difficult. So it says, well, actually, I didn't read the first part. Coordinate proof involves placing geometric figures in a coordinate plane. You use variables to represent the coordinates in a coordinate proof. The results are true for all figures of that type if I have variables representing the coordinates. If I plug in a very particular set of coordinates, I only prove it for one case, not the infinitely many cases of that shape. So it says, place each figure in a coordinate plane in a way that is convenient for finding side lengths. So if I'm working with a rectangle, I wouldn't want to place like, here's my rectangle. That would be like the worst, right? Like, who wants to find, no. I also, it wouldn't be a bad idea, like, why would I want to ever work with negative numbers? Right? I wouldn't want to necessarily like set myself up to have to work with negatives. So let's just make the origin. Mrs. Hillo, I know, has you guys circle the origin. Let's just make the origin the lower left and only work in the positive quadrant. So if I want to work with a rectangle, I'm going to make one of my rectangle's vertices be at 0, 0. Right? Let's see another one. Let's call this the point 0, comma A. Let's pick another point over here. A is a variable that could represent any potential particular location along that axis. Let's see, here's another value. I could call this B, comma 0. And so this length of the rectangle, how long is that? For my rectangle? A. That is A units long. You guys see that? That this is A units long? Yeah, I missed on that.
So technically you could put it all the way up there.
Yeah. I haven't labeled my scale. So A could be 1,000,000, A could be pi, or A could be Google. And what is this distance? That's just plain old B. So question, for the fourth point of my rectangle, what coordinates are this point?
Oh,
I actually set us up poorly because our tendency to go for alphabetic order. B is the x coordinate and A is the y coordinate, yeah. And so then I would have a rectangle. Yay! Wow, positive reviews. If you like this, feel free to go to my YouTube channel and give me a thumbs up. Some likes and subscribes. All right, how about for a scalene triangle? Scalene, what does that mean again?
none of the sides.
None of the sides are congruent, okay? So let's see. So I'll might as well set myself up working in the positive quadrant. Let's make one of our vertices 0, 0. And it, regardless of my triangle, do you guys agree that it would be possible to have one of the sides of my triangle fit along one of the axes?
Yes.
Right? Like even if it's obtuse, like whatever it is, like it's possible to rotate it and translate it so that it conveniently lands with one of the sides along the axis. All right? So let's set up one of our triangles that way. Let's see. I haven't labeled the point yet, but we still can. Where would, now if this is scalene, these coordinates will be unrelated to each other. Let's just call this like D, comma 0, right? So it's over D units. And the coordinates here cannot be related to D, so we'll just call it F and G, perhaps. Let me use my ruler because I know I'm going to be terrible at this. All right, so now in my case, my triangle, right, looks like a particular one, but imagine if I drag the point FG over here, it'd be possible to get an obtuse triangle, right? You could imagine a whole bunch of different ways that this could have been drawn, but because I have variable coordinates and I've set myself up with as many coordinates, having 0 for them, it would be very easy to work with this sketch. All right, question? Yeah, we could have named that a bunch of different ways. All right, so let's look at example 2. Question, yeah, Lily?
You still refer to it as a y-axis?
Yeah, I mean, Yep, I mean, yeah, we're just throwing it on our coordinate plane as we want to. So guys, let's say, now for this problem, this is not representative of all possible triangles. This is a very particular triangle because these points have actual numerical coordinates instead of variable coordinates. It says, write a plan to prove that SO, so here's SO, bisects angle PSR, PSR. So I want to show that these two angles are congruent to one another. All right. So if I want to show that those two angles are congruent to each other, I actually don't have, at this point until pre-calculus, I don't have a great way of measuring angles on the coordinate plane. But maybe if I could prove that these two like back-to-back triangles are congruent to each other, maybe I could use some CPCTC to prove that. So let's see, I would be able to say that SO is congruent to itself by reflexive. Right? I could then, what other information could I find?
That SOR is 90 degrees.
You could show that's 90 degrees. How could you go about showing that angle SOR is right? There might, I mean, the fact that that happens to be vertical and horizontal, we might be able to prove that. You also could do it by relating the slopes. My reason, I guess, would be that horizontal and vert lines are perpendicular. Okay, but if these weren't conveniently horizontal and vertical, I could actually find the slope of one and the slope of the other. And how would their slopes represent? Do you remember? Perpendicular lines have what kind of slopes? Slopes that are opposite reciprocals? Yes? No? You guys remember that? For the same reasoning, I could show that SOP, is a right angle for the same reason. Okay? And then I could say that those angles are congruent to each other. Oop. SOR is congruent to angle SOP by right angles congruence theorem. Right? So I've just proven that these two angles are congruent to each other. What else would be helpful for me? Right now I've got a side and an angle. It's a right triangle, so I could use hypotenuse leg. But what would I need to know? I'd need to know two segments are congruent. How could I find the length of those segments on a coordinate plane? Yeah, I could show that SP is congruent to R or SR and I would use the distance formula. And then def of cong. Right? If their lengths are the same, then the segments are equal. So I could just straight up use the distance formula and show that. And then I'd be able to say, oh, these triangles are congruent. Let's see, SOR and SOP. Oop, triangle symbol. SOP. Looks like hypotenuse leg. And if those are congruent, now I could prove, oh, let's see, I could prove that angle PSO is congruent to which angle? RSO. Now I proved the triangle's congruent. Those angles are congruent by CPCTC. One of the benefits of knowing triangles congruent is I know that all of their corresponding parts are congruent. And then I could say that SO is a bisector, or SO bisects angle PSR. Pretty much like def of angle bisector. All right. Everything good, Isaiah? Right? Yeah, these are, yeah. This is a long example. All right. But I could use, right, kind of all my old theorems and properties and postulates and just use them on the coordinate plane, and it would work out. Let's see, let's take a look at example 3.
No.
All right, example 3. So place an isosceles right triangle in a coordinate plane. All right, so did I give you guys a coordinate plane or?
Yeah.
Oh wow, I'm so generous. Coordinate planes for everybody. All right, so place an isosceles right triangle in a coordinate plane, then find the lengths of the hypotenuse, okay, and the coordinates of its midpoint M. All right, what would the best way, so I could place an isosceles right triangle this way, but I don't think that's as helpful. Let's rotate that so that the right angle actually lines right up with that X and Y axis. I think that would probably be the easiest way. Right? You guys agree? Let's see. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So we'll do that, and then let's see. 3, 3, 3. All right. So isosceles right triangle. It's going to look something like that. Oh, no, you didn't. No, you didn't. That would have been awesome if it just happened to line up. And now if I want this to apply to all possible right triangles, I want their points to be generically labeled. Okay? So we could call this 0. We could call this P and Q. You could come up with better names. 0 happens to be at, or O, point O, my bad, is the point 0, 0. Point P we could call 0, comma, some letter, question, comment?
Make a Q with W.
For like POW?
Pretty close.
For WAP?
No.
No? Well, anyways, we'll just call this 0K. You could have come up with some other letter. We'll call this, oh, wait. Guys, if this is K units, how far is this?
Going.
That's also K units, right?
Oh yeah.
So what's the ordered pair here going to be?
K out.
Wait, why?
K-O. Wow, that's pretty great. All right, if this is isosceles, I knew that this was K units away, and this would be K units away. All right, yeah. So I could have like oriented this triangle a bunch of different ways on my coordinate plane, but I want to do it in a way that's going to be most helpful. So what I'm interested in now is I want to figure out this length, and I'm going to do it generically using those points, and then I'm going to find the midpoint of it, which we'll call point M. So let's label our points, x1, y1, and x2, y2. And to find the distance between 2 points, you guys, are you familiar with the distance formula? You guys have it memorized? You keep a copy of it in your wallet? So let's see. So the distance, which I'll call PQ, is going to equal the square root of, let's see, y2 minus y1. Or sorry, man, I'm so like slope formula thinking. My bad. I've been doing slope all morning. So x2 minus x1, so k minus o squared.
How would you find the midpoint?
Oh, we'll get there. We'll get there. Don't you worry.
Well, shoot.
All right. So I just plugged in the coordinates for the distance formula. And this is all in terms of variables, but that's fine. We're fine with that. So let's see, the square root of k minus 0. What's k minus 0?
Okay.
K. 0 minus k is negative k.
Okay.
And let's see, so that's going to be the square root of k squared plus the opposite of k all squared will be positive k squared. You guys agree with that?
I feel like I changed the form.
When you square a negative, it becomes positive.
There's no parentheses.
All right. K squared plus k squared is 2k squared. 2k.
I see.
And let's see, where's my scroll bar at? And let's see, I could simplify this a little bit. I could factor out the k squared. Have you guys done any radical work in a long time? Did you do that? You did do some properties of radicals in Algebra 1?
The last 2 weeks.
Nice. So let's see, the square root of k squared we'll call k. In our case, it's a distance.
I don't remember that.
And the square root of 2 I can't simplify. So k roots of 2 is the distance between those points. So k roots of 2. Oh yeah, everyone likes numbers better than letters, but that's why everyone loves math more than English, right? Because numbers are better than letters? No. All right, the midpoint formula. Does anyone know the midpoint formula?
Oh,
yeah, it's a
X2 minus X1 over.
Yeah.
The midpoint formula doesn't give us a number, it gives us an ordered pair. And it is the average of the x's and the average of the y's. So let's plug in to find the midpoint, which I guess we called m in this case. And actually equals is probably not even appropriate. Sometimes I just do like a colon there or whatever. So m is the point, let's see, x1, x2, so that was 0 plus k over 2. y1 and y2 was k plus 0 all over 2. And what's the midpoint simplify to be?
Okay, over 2. Okay, over 2.
K over 2 and k over 2. Right, that's 0.
Oh, that's 0 now?
Yeah.
Oh.
Yeah. All right, so here's there is the midpoint. So it is possible to work within a coordinate plane and to be able to do proofs. All right, and to be able to find distances and to be able to do all of these wonderful, wonderful things. Let's try example 4. We'll close out on example 4. All right. Oh my goodness, friends. Oh my goodness. All right, so here it says write a coordinate proof. Coordinates of vertices of quadrilateral O2UV have been given to us. Okay, check this out. Let's see first of all if this makes sense. What is this distance? Isaiah, what are we thinking? What is this distance, guys?
H.
H. Okay. Now this distance is M, sorry. Right? It's M to that point. And adding an H to the M coordinate gives me M plus H. Right? If this is M and this was H, then the X coordinate of that point would be M plus H.
Wow.
Do you see that? Blessings on you. All right, so I just want to point out that, all right, it was labeled as a quadrilateral, but it looks like they specifically gave us a quadrilateral that was a parallelogram, which I can't wait until I could prove all sorts of things about parallelograms for you. Does anyone know how high this parallelogram is?
Okay.
No.
It is K units high.
Wait, I didn't so.
All right, yeah, no, all right.
Oh, 6.
Okay, no worries, no worries. Let's see. Does this, okay. So as far as a proof, I've got my given information, right? Right, I've got my given information, which were all these coordinates. If I want to prove these two triangles are congruent, what ways could I do that? Reflexive property. What is congruent to itself by reflexive?
OU.
OU, guys. Boy. Oh boy. All right, so OU is congruent to itself. I believe I've shown this, but let's actually prove that. I'm going to say that OV, the distance for OV is going to equal the difference, the absolute value of the difference of their x coordinates.
Where's the V? That's the point. Oh, I see it now. Okay.
All right, which is H. This is the one-dimensional distance formula.
Is that why it's absolute value?
Yeah. All right. One-dimensional distance formula is just the absolute value of the difference of those points. So I'll just call this distance formula. Right. Does anyone know how I could find the distance from T to U? Or U to T? That would be the absolute value of the difference of its x coordinates. Here, I'll even highlight those a little different. Okay, so I'm going to have m plus h minus m. What happens when I subtract those m's?
H.
Yeah, it's just going to equal h again. Also true by the distance formula. I'm going to say that OV equals UT by transitive property. All right. And then they are congruent to each other. And why are they congruent? Def of Kong. Man, Haley with the save.
Yeah.
Def of Kong. All right, so these are congruent to each other. Wow. Now I could do some like diagonal distance formula, but I'm rather not going to do that. Do these lines appear to be parallel to each other?
Yes.
I think so. I'm going to say that line TU is parallel to line OV. And I'm just going to say as my reason, horizontal lines are parallel.
Is that okay reason to give on the test?
I think so.
Will there be a lot of this kind of proofs on the test?
No, no,
Okay.
no.
This is like me.
No. All right, if those lines are parallel, how does that help me? What can I say about angles? Which angles are going to be congruent?
Let's see. 10, 2,
This angle and this angle,
yes.
right? Why are those going to be congruent? Yeah. So let's see. So angle TUO is congruent to angle VOU by alternate interior angles theorem. Right? So it's weird doing proofs on the coordinate plane, but I just want to point out it is feasible. It is possible. And do we have enough information to prove triangles are congruent? Triangle OTU is congruent to triangle UVO. How are those triangles congruent? No.
No, it's side. No, it's angle side.
Side.
Side angle side.
It's
Yeah, side
It's
angle side. Yeah. Is that now?
Right, because the angle is included, the included angle between the two sides that I have congruent. All right? Whew, my goodness. Well, thanks for hanging in there, Internet friends. Have a great day.